Hi everyone, this is the test review video for our Chapter 2B test coming up at the end of this week and beginning of next week. So part 1 of your test is going to be on Friday the 16th, and we'll be reviewing in class on Wednesday and Thursday before that. Part 2 of your test will be on Tuesday the 20th, and we'll be taking Monday the day before to review in class as well. You may use a calculator on both parts of this test, but like the last one, you're going to have to support your work algebraically if it's not a calculator problem. And then there will also be a bonus question on the day 1 part of the test. All right, let's get started. Part 1. So this is what you're going to see on Friday's portion of the test. In the first group of problems, we are going to find the domain of the following function. So remember, there's two things that create a domain restriction: a 0 in the denominator or a negative number under the square root. So if we're looking at function f on the left here, you'll notice we have a square root. We want to make sure that that square root, or what's underneath it more specifically, is greater than or equal to 0. So you can set up an inequality here to solve for your domain. We're going to add 6 and then divide by 3. Nowhere here did I multiply or divide by a negative, so I don't have to switch my sign. So my domain is x values greater than or equal to 2. Make sure all domains or ranges on the test you're putting in interval notation. So we write that in interval notation, bracket, because we're equal at 2 all the way to infinity. Function g now. This one has a denominator. Your denominator cannot equal 0. So again, to solve, in this case we're solving for the restrictions, we're going to take our denominator and say it cannot equal 0. We have a quadratic, we can factor it. Here we have a trinomial, so we're looking for two numbers that multiply to negative 18 and add to 3. That's positive 6 and negative 3. And then if I set each of those parentheses equal to 0, I'll get my two restrictions at negative 6 and positive 3. So my domain is all real numbers except for those two values. So how we write that in interval notation is negative infinity to negative 6 would be the smallest number, or what I encounter first as I go from left to right on my number line. Then negative 6 to 3. And then 3 to infinity. Notice it's all parentheses there because infinities are always parentheses, and negative 6 and positive 3 we cannot equal. All right, finally, let's look at problem H. We have a radical in the numerator, so that piece tells me that x must be greater than or equal to 0, and we'll come back to that in a minute. In the denominator, x squared minus 5x minus 14 cannot equal 0. If I solve by factoring, put an x in front of each parentheses, I'm trying to find two numbers that multiply to negative 14 and add to negative 5. That's negative 7 and positive 2. If I set each of those equal to 0, I get that x cannot equal 7 and x cannot equal negative 2. So we've got three pieces that we have to worry about here. X must be greater than or equal to 0, so I'm going to graph that on a number line first here to be able to kind of visualize it. So that would be 0 and everything above it. X cannot equal negative 2, which that actually is not in our domain anyway, so that doesn't affect anything. And x cannot equal 7, so we will have an open circle at 7, which means the numbers in my domain are in two groups, between 0 and 7 to infinity. So putting that in interval notation, my domain would be 0 to 7, 7 with the parentheses, and then 7 to infinity. Question number 2 on your test will be a piecewise function, and you're going to have to evaluate some things within that piecewise function. Remember, if a number is inside the parentheses, it's an x. If a number is outside the parentheses, it's a y. And really what you're trying to do here is just find the other half of a point. If you're given the x, you're finding the y. If you're given the y, you're finding the x. For example, if I have g of negative 4, I find negative 4 for an x value on my x-axis, and then we go either up or down to get to my graph. In this case, I would have to go up to +2 would be what that evaluates to. G of 0, 0 on my x-axis would be the origin, and then we go up or down to get to the graph. In this case, I have to go down to -1. If I go down further, I don't actually hit a value on the function because I have an open circle there, so we don't have to worry about that. G of 4 is the next one. I find 4 on my x-axis. In this case, I go up to my graph. That's 1. And then we have another piece to evaluate here, G of -2. So I find -2 on my x-axis, and I have to go down to -1, it looks like. Bring down my sign, 1 minus -1. My final answer is 2. For part D, find x when g of x equals 1. So here we're given a y and we're trying to find the x that goes with it. Remember, this type of problem, you could have more than one answer, so you want to look both directions on your graph. When y equals 1, that's there on my y-axis, and then we actually have two answers here. If I go to the left, it looks like it's approximately -3.5. If I go to the right, x equals 4 is a value on the graph. The next one, find x when g of x equals -4. Again, y equals -4. Y equals -4 is right here. And if I go left and right, there are no values of the graph in either direction. At the axis, remember that's an open circle, so there is no point there. So does not exist, or you could just say no solution. Question number 3, for the following function, we want to find any min or max values, and then we want to find where the function is increasing, decreasing, or constant. For this, you're going to need a graphing calculator. So I'm going to bring my graphing calculator up here. Okay, we're going to go to y equals, clear out anything that's in there, and type our function in. X to the 4th minus 5x to the 3rd plus 5x squared plus 5x minus 6. And then we can just graph this on our standard window, zoom 6. And there is our graph. Let's see if I can drag that over. There we go. Okay, we want to find any min or max value. So hopefully you're looking at this saying, okay, I think there's 2 mins and 1 max. Let's start with the minimums. Second trace, minimum is number 3. Close to where that's blinking right now is a minimum. So let's use for a left bound, maybe -2 is on the left side of it. And it looks like 0 is on the right of it. Doesn't have to be those exact numbers, but something close to that. Guess, hit enter one more time. And there's the minimum. We'll come back to that. I'm just going to drag it again over to the screen here so we can save it for later. Okay, let's continue. Let's get that other minimum. Second, calculate. Number 3. The other minimum looks like it's happening between 2 and 3. So I'm going to choose a left bound of 2 and a right bound of 3. Enter. There's that minimum value. Let's drag that over for later. And then one more. We're going to get the maximum. Second, calculate. Maximum number 4. I would say the maximum looks like it's showing up between 1 and 2. So left bound 1, right bound 2, guess. And there is my maximum. All right, so let's go ahead and list what each of those are. Done with the calculator for now. And I'm going to round to the nearest hundredth, 2 decimal places. So I have a maximum at 1.47 and 0.94. I have a minimum, if I'm looking at the one that's on the top right over here, at -0.33 and -6.91. And then I also have a minimum, if I'm looking at the one that's on the bottom right, at 2.61 and negative 1.38. Part B, we need to find where the function is increasing, decreasing, and constant. So there are two intervals where your function is increasing, and that's where it's going up from left to right. Make sure you're always reading these graphs from left to right. That is happening, and you can use these mins and max values to help you, between the minimum point we have at negative 0.33 all the way to the maximum at 1.47. And then again, it is increasing between the minimum we have at 2.61 all the way to infinity. Again, always x values, always parentheses on these. It is decreasing on the far left from negative infinity to negative 0.33. And then it is also decreasing between, let's see, 1.47 and 2.61. There are no intervals where this function is constant, where you would have a horizontal line. Okay, question number 4, we are determining if the following functions are even, odd, or neither. So quick review, even is symmetry to the y-axis. Odd is symmetry to the origin, and that looks like a rotation of 180 degrees, and of course neither is neither. So if we're looking at all three of these graphs and trying to determine if it's even, we're looking for one that has symmetry to the y-axis. You can see that the one on the bottom here is even. And again, your explanation, if you had to justify it, you could just say symmetry to the y-axis. If we want a function that's odd, we're looking for one that if we turn it upside down, it looks exactly the same. And if you look at this one that has the kind of U shapes on it here, you can turn it upside down on your paper in front of you, or flip your head upside down, do a headstand to look at it, and you'll see that it looks exactly the same. So we would say that this function is odd. And again, our justification would be symmetry to the origin. And then if we look at the one on the left here, this one's a little tricky because it looks like you might have symmetry to the y-axis, but if you flip it over the y-axis, because this point I've labeled here is not on the y-axis, it won't quite look the same. That point would actually end up over here, so you would have something that looks close, but a little bit different. This is what our reflection would look like. So this guy is going to be a neither. And if you had to explain, I think I spelled that wrong. No, I didn't. If you need to explain that, you could say there's no symmetry to the origin or the y-axis. All right, number 5, we're going to use a piecewise function to evaluate. So the piecewise function is given over here. Instead of an x, we have a t. We'll start with f of negative 2. F of negative 2, we have to first determine where we're allowed to plug that in. And negative 2 is one of our breaking points, but we want to plug it in the function where we're allowed to equal negative 2, so that would be the bottom piece. Negative 2 to the third over negative 2 plus 9. That would be negative 8 on top, 7 on the bottom. That fraction does not reduce, so we're just going to leave it as the exact answer, negative 8/7. Remember, don't round that stuff, just leave it as the fraction. Negative 8, I need to figure out where that one is going to lie. So it's not bigger than negative 2. I'm not going to use the bottom one. It is between negative 10 and negative 2. So I'm going to use the middle part of my function. Negative 8 plus 19 gives me 11. And then one more, negative 13. You're probably going to guess this one actually uses the top piece. It's a number smaller than or equal to, smaller than in this case, negative 10. So we're going to plug it in. Negative 13 squared minus 5 times negative 13. And you can type that all in your calculator if you want. Negative 13 squared is going to give me 169. 5 times 13 is going to give me 65. And then if I add those together, 169 and 65, I get a grand total of 234. On to question 6. Question 6 will be similar to what you guys saw on the take-home quiz. You need to know your parent functions chart, which was one of our big ideas papers. It was, if you were in class, the one I copied on white paper. This question is going to give you 3 properties, and you have to list all the parent functions that have that property that are on your paper. So here are some examples of what those would look like. If we want a function that is odd, if you're doing this at home right now, you could take out that paper and you can list all of the ones that are odd, but you want to make sure you kind of picture those in your head as well. Those functions are the identity function, which is the equation y equals x. These are all the ones that, again, have that symmetry to the origin. The next would be the cubing function, then the cube root function, the reciprocal function, and I believe that is all of our odd functions. Next, we want to know any function that has part of its graph in quadrant 3. Again, that is the identity. Actually, all of the ones from above, the cubing, the cube root, and the reciprocal. I'm just going to run through the list of the other options here. Squaring is only in quadrant 1 and 2. Absolute value is only in 1 and 2. Constant, I'm going to write constant could be, depending on what the value is. For your k value, it could be, y equals -8, and then that would be in quadrant 3. So that's a maybe. Square root's only in quadrant 1. Reciprocal squared is in quadrant 1 and 2. Logarithmic is in 1 and 4. Exponential is in 1 and 2. And logistic is in 1 and 2. Finally, has a y-intercept at 0. Again, that is the identity function, the cubing function, the cube root function. Reciprocal does not have a y-intercept, neither does reciprocal squared. Other functions are the squaring function. That does have a y-intercept at 0. The absolute value has a y-intercept at 0. The constant, again, could be the square root function has a y-intercept at 0. We got cube root already. Logarithmic has a y-intercept that's an asymptote. Actually, it has an asymptote on the y-axis, so that's a no. Exponential has a y-intercept of 1, and logistic will have a y-intercept of something between 0 and the L value that's used. So again, it won't be at 0 because that's an asymptote. Okay. Number 7, name the transformations that produce the graph of G from the graph of F. So for this problem, you're going to want to remember this nice little chart that was part of the notes where the brackets represent one of our parent functions. There we go. Something like that. Oh, and there was a negative in front of my B also. Remember that on the inside here, if something is in front of your x, you want to factor it out first, otherwise it might mess up your left-right shifts. So for example, if I'm looking at function g here, that 3 in front of the x needs factored away from the x. It's still going to be inside the absolute value bars, but I need a parentheses to separate it from the x, so it'll be 3 quantity x plus 3 when I factor it away from that 9. Okay, so now naming my transformations. I'm just going to go from left to right, the things that are different in the function g from the original function f. The negative out front will be a reflection over the x-axis. The 1/4 out front, that's our a value, will be a vertical shrink, and if you wanted to say by a factor of a 1/4, that's fine. The 3 on the inside is a horizontal shrink. Remember, that one was weird. If it's a number larger than 1, it shrinks. If it's a number smaller than 1, it stretches. The plus 3 on the inside is going to move the graph left 3. And then finally, the minus 5 at the end will move it down 5. Okay, let's do the same thing for the next one. Again, for this cubing function, you can see that I've got a number in front of the x. Actually, it's a -1, so I'm going to factor that out. So I'm going to say 2. I'm going to create a bracket here, get that negative away. That's going to be x minus 4. That's all still cubed, plus 3. Okay, again, let's run through our transformations from left to right. The 2 out front will be a vertical stretch, technically by a factor of 2. The negative on the inside will be a reflection over the y-axis. The -4 will move us right 4. And then the +3 at the end will move the graph up 3. And there are all your transformations. Okay, that was the end of what you're going to see on part 1. Let's move on to part 2. Again, this is what you're going to see on Tuesday the 20th. Problem number 1, determine if the following functions are even, odd, or neither. Justify your answer. And because we have the equation here, we want to justify algebraically. So we're going to start by plugging in -x. And we're looking for one of two things to happen. If we plug in -x and it simplifies to the original function, it's even. If we plug, ignore the bell. If we plug -x into the original function and you end up with the opposite of the original function, it's odd. And of course, neither would be neither. So let's look on the first one here. -x to the 4th minus 2 times -x squared plus 4. So that'll be a positive x to the 4th. -x squared is positive times -2 is a -2x squared plus 4. And you can see that does simplify to my original function f of x. So f of -x equals f of x. Therefore, we can say that this is an even function. Let's look at the next one on the top right. Again, we're going to start by plugging in -x. -x to the 3rd plus 5 times -x minus 2 all over 4 times -x. -x to the 3rd is negative times the negative out front is positive x to the 3rd. Then I'll have a minus 5x, a minus 2, all over a negative 4x. The numerator is not quite the same as my original function, and even if I factored a negative out, it still wouldn't match that numerator. I would still have this -2 that kind of is the oddball there. So there's nothing we can do to make this look like the original function or the opposite of the original function. So this is a neither. Remember, sometimes these fraction ones can be a little tricky. You want to make sure if you could factor maybe a negative out of the numerator or denominator or both and get it to look the same, then it could be either even or odd. Finally, let's look at the one at the bottom. Again, I'm going to plug in -x. So f of -x equals -x times the square root of -x squared minus 1. So that's -x. Inside my square root, that simplifies to a positive x squared minus 1. And you can see, even if I put parentheses here, maybe that emphasizes it, comparing that to the original function, it's the same as the original function with the negative out front. So it simplifies to negative f of x, f of -x, simplifies to negative f of x. That's what we're looking for. Therefore, it is odd. Please, 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 when you do this test, make sure you are showing this algebraic work. The graph of this could give you a hint, but the graph is not a proof if you're given the equation. On the first part of the test, we had to use a graph because that's all we were given, but if you have equation, you must show it algebraically works for every point, not just what we're seeing on our viewing screen in the calculator. Number 2 is an average rate of change problem. Remember, this is just our slope formula in disguise. We're given two x values here, -3 and -5. So we have half of 2 points that are on this function. We want to evaluate the function for both of those values to get the y's that go with them. So we're going to plug into the function -3 and -5. And you can use your calculator for that. -3 to the third minus 4 times -3 squared plus 1. So that's going to give me -27 minus 4 times 9, so minus 36, plus 1, I get -62. If I plug in -5, -5 to the third minus 4 times -5 squared plus 1. -5 to the third is -125. -5 squared is 25 times -4 is -100, so minus 100 plus 1, I get -224. So those are the y's that go with these x's. Let's fill those in. -62, -224. From here, rate of change is just going to be my slope formula. So y minus y over x minus x. So -224 plus 62 on top is going to give me -162. In the denominator, -5 plus 3 will give me -2. And then if I divide, I'm going to get a positive 81 is my average rate of change. Question number 3 is difference quotient. So I'm going to write down our difference quotient formula here for you. Make sure you know this for the test. So usually we use an F. I'm going to use a P because we have function P here. It's going to be P of x plus h minus P of x all over h. So the first thing that we need to find is P of x plus h, which means take the x out of the function, put x plus h in its place. I'm going to FOIL first. X squared plus 2xh plus h squared. I'm going to distribute my 6 in while I'm at it. And then I also have to distribute that negative in. Make sure you always FOIL before you distribute. Negative x squared minus 2xh minus h squared plus 6x plus 6h plus 7. All right, so now to do the difference quotient, I'll just put DQ for difference quotient. It's going to be that whole P of x plus h. Just copy that down. Minus my original function, negative x squared, positive 6x plus 7. Put it all in parentheses. All divided by h. Next thing we do is distribute our negative through, and I'm not going to rewrite all this. I'm just going to make it a plus and change all my signs. Positive, negative, negative. The next thing we can do is cancel out anything in the numerator that we can. So we have a negative x squared and a positive x squared, a positive 6x and a negative 6x, positive 7 and a negative 7. So I'm left with negative 2xh minus h squared plus 6h all over h. And then everything here is divisible by h. So my final answer is negative 2x minus h plus 6. It's our difference quotient. Number 4, we need to write the equation for the piecewise function that's shown. So let's call this function f of x. And it looks like I've got 2 pieces. So I'm going to have 2 equations I'm going to need to fill in here. And also, don't forget the domain where that part of the function is located at. All right, so let's start with the parabola that you see there. I'm going to label some points on the parabola. I've got 2, 0, 1, 1, 3, 1. Hopefully you can see that's just our regular y equals x squared that looks like this, that's been shifted to the right 2 units. So if I take x squared, that function, and shift it right 2. So think about your transformations. Moving something to the right 2 is a minus 2 inside the function. So it's going to look like that. Now remember, the y equals is already written up here for us, so we just need to put x minus 2 quantity squared in for the right side of the equation. And you could always FOIL that out if you want to. There's different forms you could write that answer in. That piece of the function is showing up to the left of 3. Let me erase my little dots there for a second. There we go. So to the right of 3 is all of my x values less than, let me get my red pen back, less than or equal to 3 because we have a solid dot there. And I just noticed, I think we should have an open circle here, otherwise we don't pass the vertical line test. So let's say that's an open circle. For the other part, we have a line, so we're going to think y equals mx plus b, and there's 2 things we need to know for this equation. Number 1, what's the slope? And you can count rise over run here. You have to rise 1 and run 1. So your slope is actually 1. To solve for the y-intercept, you can pick a point on the line, so maybe 4, 6, since I have that one marked. My y is 6, my x is 4. That means b must equal 2. So my equation of the line is y equals 1x plus 2, or you could just say x plus 2. Again, we don't have to write that y equals. That, if we say there's an open circle on the left, is only values greater than 3, where we see that piece of the function. Let's move on to number 4. Here you are graphing the piecewise function. So I'm going to make an XY table. I'm going to do this how we did in class. This says 6 parts to my table, 6 points. I like to pick 3 x values for each piece, so I'm actually going to put 9. I'm going to overdo it a little bit here. And then after we get the graph, we can talk about it being continuous or discontinuous at those breaking points. So the 3 parts of this function are y equals x squared plus 5, y equals 2x minus 1, and y equals negative 6. Numbers that I can plug into the top piece are all values less than negative 3. So make sure you include negative 3 in that. Negative 3, negative 4, and negative 5 I'm going to use. And I'm going to make a note to myself that negative 3 when I graph it, because it's not equal to, we use an open circle at that point. 2x minus 1 is all the values between negative 3 and 4. So I'm going to pick like negative 3, 0, and 4. Again, it's important to include those end values. You can always pick more than that if you want. Negative 3 when I graph it will be a closed circle. 4 when I graph it will be an open circle. And then finally, y equals negative 6 is all values greater than 4. So I'm going to pick 4, 5, 6. 4, that breaking point will be a closed circle. Okay. So let's plug these numbers in. The top 3 are going to go into x squared plus 5. So negative 5 squared is 25 plus 5 is going to give me 30. Negative 4 squared, that's 16 plus 5. That's going to give me 21. And negative 3 squared is going to give me 14. I might have to count by 2s or something like that on this graph. 2x minus 1, if I plug in negative 3, I'm going to have negative 7. If I plug in 0, I'm going to have negative 1. And if I plug in 4, I'm going to have 7. Finally, y equals negative 6. There's no x there, which means it's a horizontal line. And no matter what x value I have, I'm going to get negative 6. And again, let's count by 2s on our graph to get everything to fit here. Sorry, that turned out a little gross. So let's see, negative 5 would be here. And then I need to go up to 30, which that'll be pretty high. That'll be like 15 on this graph. So that one's off a little bit. Negative 4 will be here on my graph. And I want to go up to 21. So it's just going to be right above my graph. And negative 3, I'm at 14, which would be 7 units up. 1, 2, 3, 4, 5, 6, 7. That one is an open circle. And we know that that's part of a parabola. So you're going to make a curve shape, arrow up and to the right. All values to the left. All values smaller than negative 3. 2x minus 1, I have points at -3, -7. So 2, 4, 6, -7 is going to be right there with a solid dot. 0, I'm at -1. And then 4, I'm at, again, a +7. 1, 2, 3, 3.5. There we go. And that one's an open circle. Let's get my open circle there. What was I at? 4, 7. There we go. And that's just a line. Y equals mx plus b. Do best there. Here we go. Okay, and then finally, I have a horizontal line at y equals -6. Starting at 4, I'm at -6. 5, I'm at -6. 6, I'm at -6. And that is defined for all values greater, so it's going to go forever to the right. Finally, we want to state where any places where this graph is discontinuous, meaning an x value where if I want to trace it from left to right, I'd have to pick up my pencil to jump from one piece to the next. I have breaking points at -3 and at 4, and you can see in the table here, -3, I do not get the same value out, and 4, I do not get the same value out. So you can even just look at the table and say discontinuous at x equals -3 and x equals +4. Or you can see that on the graph as well. At -3, it jumps from one piece to the next, and then again at 4, it jumps from one piece to the next. So we say that it is discontinuous there. On to question number 6. This is our combining and composing problem. So let's start with part A, function c and d here that I'm using. C minus d of x, remember that means the same as c of x minus d of x. So function c minus function d. 4x squared minus x plus 3 minus function d. I'm going to put in parentheses because remember you need to distribute. Parentheses never hurt anything. I'll have a minus 5x and a +1. And then combine my like terms. 4x squared, -6x, +4. Part B, I need to multiply function c times function d. Again, I'm going to put them in parentheses. 4x squared minus x plus 3. And I know this is multiplication, not composition, because that circle is closed, not open, by the way. Here we have to multiply everything in the first equation by everything in the second, or everything in the first parentheses, excuse me, times everything in the second. So this is like an extended foiling problem. 4x squared times both things in the second parentheses will give me 20x cubed minus 4x squared. Negative x times each term in the second parentheses will give me a -5x squared and a positive x. And finally, 3 times everything in the last parentheses will give me a 15x. minus 3. Again, combine like terms. Final answer here is going to be 20x cubed minus 9x squared plus 16x minus 3. Part C, we have that double parentheses, which tells me now we are composing. I like this notation because I think it's easy to see that you're plugging D into C. So I'm going to take all of function D and put it into function C anywhere I see the variable. So that is going to look like 4 times 5x minus 1 squared minus 5x minus 1 plus 3. We FOIL first. 25x squared. You'll have a -5x and a -5x, so -10x plus 1. Bring everything else down. Oop. Drop my parentheses in the wrong spot there. Don't do that. Parentheses 5x minus 1. There we go. Then I'm going to distribute the 4 and the negative through. So I'm going to have 100x squared minus 40x plus 4 minus 5x plus 1 plus 3. And then again, combine like terms. Final answer will be 100x squared minus 45x. And then 4 plus 1 plus 3 will give me plus 8. On to part D is just the opposite. We are plugging C into D. Notice the open circle tells me composition, and you can always write it like this if you need to, with the double parentheses. So C into D will be all of function C into function D, where I see that x. That looks like 5 times 4x squared minus x plus 3 minus 1. Distribute the 5 in, 20x squared minus 5x plus 15 minus 1. And then combine like terms. 20x squared minus 5x plus 14. The last two problems here are just evaluating problems. We did something similar to E on a graph earlier in the part 1 part of our test. Let me get a different color here. We'll do purple. C of negative 5, let's do that first. So plugging negative 5 into function C. Everywhere I see the x. And again, you can use your calculator to help you evaluate that if you need to. I'm going to have negative 5 squared 25 times 4 is 100. Plus 5 plus 3 will give me 108. Then I want to do D of 4. So 5 times 4 minus 1, which will be 19. And then the function notation tells me to subtract. So I'm going to do 108 minus 19, which will be 89, is my final answer. Okay, last but not least is an evaluating problem. Oh, I ran out of colors. That's so disappointing. Let's go back to blue. If you have these double parentheses, you want to start from the inside out, remember. So we're going to start with C of 1. So I'll kind of do that to the side here. 4 times 1 squared minus 1 plus 3. That's 4 minus 1 is 3 plus 3 gives me 6. So now I can say that whole C of 1 simplifies to 6. We plug 6 into function D. 5 times 6 minus 1, 29 is my final answer. Okay, we have 2 more problems. Problem number 7, I've got a couple of them here. You're only going to have one on the test. You need to find the inverse and then name the domain and range of the inverse. So to find the inverse, g of x, let's call that a y. We're going to switch the x and y. And then we're going to solve for y. So I'm going to subtract 4 first. Don't forget to bring that negative down. Then I'm going to divide everything by negative 1. That'll give me a negative x plus 4 equals the square root of y minus 5. Square both sides, so negative x plus 4 squared, and that cancels out my radical. You can FOIL that if you want to, but there's not any specific form that we need this to be in, so if I were you, I wouldn't, because it's less likely to make a mistake. If you have less, you have to simplify. Finally, add 5. Don't forget at the end, put back in your function notation. So that original function was g of x. We put the little negative 1 there to state what we have now is the inverse. As far as domain and range go, the domain of the inverse, if we're looking at the inverse function, there's no value that x cannot equal. So that is all real numbers. The range is the domain of the original function. And the original function had a radical. So we're going to look at x minus 5. We want x minus 5 to be strictly greater than or equal to 0. So that means the x has to be greater than or equal to 5. Which means now my range for my inverse will be 5 to infinity in interval notation. Let's do the same thing for h. I'm going to start by flipping my x and y. So again, think of that as a y. X equals 4y cubed plus 2. Solve for y. Subtract 2. Divide by 4. I'm just going to say x minus 2 all over 4. No need to overcomplicate this. And then to get rid of a third power, we're going to do a cube root. So cube root all over all of that stuff. Again, instead of y, I'm going to go back to my original notation with the h, inverse. The domain of my inverse cube root functions, if you think about what that looks like, that's kind of like that little S sort of sideways shape there. The domain of those is all real numbers. We're not going to have any restrictions in a cube root. So all real numbers. The range, again, is the domain of the original function that we started with. Again, no number that I can't plug in there. So all real numbers. Last problem, we are given a graph of g of x, and we want to graph function f, which is function g transformed a little bit. I think the easiest way to do this, instead of moving the whole graph, is just deal with the points that you're given on the graph. So I'm going to label these. This is the same graph, by the way, you had on the take-home quiz, just some different transformations happening to it here. So I have points at 0, 3, at 3, 6, and at 6, 0. So I'm going to make kind of like a table here when I do this. My original points are 0, 3, 3, 6, and 6, 0. Okay, now let's go back up to the function and see what transformations are happening. So there was an order of operations, if you remember, to transformations. The first thing that you do, if you have it, are any left-right shifts. Well, there's no number added or subtracted on the inside, so we don't have any of those. Next, we have a 0.5 in front of the x, which you can always write that as a 1/2, of course. So that means that there is a horizontal stretch. So we'll say horizontal stretch by a factor of 2. Now it's important because we're going to have to actually do that stretch with our points. We use the reciprocal when we name those. Next, you do any reflections. We have a negative out front of the function, so we're going to reflect over the x-axis. And then finally, we're going to move all of the points up 2. Now again, if you like to do this all in the graph and physically move the point, you can. But again, I think that the table of values is kind of nice as well. But if you're not sure how it's going to change a point, graph it, see what happens. So we have 3 transformations. 1, 2, 3. The first thing that we need to do is a horizontal stretch by 2, which means that we're going to be twice as far from the y-axis. When we have a horizontal stretch, we're going left and right. So 0, 3 is on the y-axis. It will remain on the y-axis. 3, 6 is going to be stretched twice as far. Well, right now, it's 3 units from the y-axis. So if I go twice that distance out, it's going to change to 6, 6. And then 6, 0, again, if I went twice the distance from my y-axis, it's going to end up at 12, 0. The next thing we do is reflect over the y-axis. So let's take our point 0, 3, or excuse me, the x-axis. Let's take our point 0, 3. If we reflect over the x-axis, it would reflect down. So you can see that it would end up at the point 0, negative 3. All that's happening when we reflect over the x-axis is it's switching the coordinate of our y value. So instead of 6, 6, we'll be at 6, negative 6. 12, 0 is on the x-axis, so it will not change. The last thing we need to do is take our points and move them up 2. So let's say I have 0, negative 3 down here somewhere. If I move that up 2 units, it would be at 0, negative 1. So you can see what changed. My y value increased by 2. Same thing's going to happen with all of our other points. Negative 6 plus 2, negative 4. And 0 plus 2 gives me 2. That last column is what we graph, and we have our transformed function. 0, negative 1 was our first point. 6, negative 4 was the second point. And 12, 2 is going to be way off the graph. Well, not way off, a little bit off the graph. I ran out of space there. And there is our answer. All right, that is the end of our test review for day 2. Remember, if you want some extra practice, there's a lot of extra problems available on Polaris. You can practice the problems you feel like are useful. Also take advantage of time we have in class the next couple of days. Pick a problem, try it. I'll check it for you. We'll talk about what you missed, ways to improve. Use me in class if you guys have questions or you feel like you need, or you're not sure how to prepare for the test, or you're not sure what you're doing wrong for things. Make sure you ask in advance. All right, thanks guys.